Hi, y'all. This is Mr. Heier again. We're going to talk about horizontal forces and mainly friction, but we're going to deal with things that are moving horizontally. All right, so break this up in a couple of sections. We're going to look at just friction, and then we're going to look at a special case known as the coefficient of friction. All right, so first of all, I just want to do a quick review of net force. Right, the net force is the sum of all the forces that are acting on an object. And then if an object is in equilibrium, that means that the net force, of course, is equal to zero. Right, so we have first just a couple of examples of using net force. 70-kilogram object is pushed with a force of 20 newtons on a horizontal surface. If the friction force is 5 newtons, draw a free body diagram and calculate the net force and the acceleration. Right, so since we're dealing, it's a 70-kilogram object, of course, we're going to deal with the weight. Right, so I'm going to draw a free body diagram. I've got a bunch of arrows. You can just draw them on your thing. So you draw your box. This is going to be FW. This is going to be the normal force, Fn, and they're going to be equal to one another because Fn is going to equal to Fw just in opposite directions because it's sitting flat on the ground. Right, and then you've got a 20 Newton force pulling to the right, so that's going to be the applied force Fa equal 20 newtons. Right, and then you're going to have a frictional force, and I'm going to make that a little bit smaller because friction is only 5 newtons. And we're going to write that as F sub F for force of friction. And that's equal to 5 newtons. All right, so there's our free body diagram. And then it's just to calculate the net force and the acceleration. Well, net force is equal to ma. So we can find net force two ways. We can do it by adding the forces, or we can multiply m times a. But we don't know a because that's one of the things we're going to look for. So the other thing is we can find the sum, right? Which in this case, all the forces, the normal force and the weight cancel each other out, so we don't need to include them. So that basically tells me it's going to be the applied force minus the frictional force, or 20 minus 5 equals 15 newtons. Right, so that's my net force, and then we know the net force equals ma, so 15 equals the mass of 70 times the acceleration. We divide both sides by 70, and we get our acceleration to be 15 over 70, or 0.214 meters per second squared. Okay, so pretty straightforward. And that's if you know what the friction force is. So let's look at another one. We got a 10-kilogram object. It's pushed at a constant velocity. Right, constant velocity means the acceleration is 0. If the surface exerts a frictional force of 9 newtons, what is the force of the object pushed? Okay, again, since we're on a flat surface and we're pushing something horizontally, our weight and our normal force are going to be the same. Right, so this is, again, Fw and Fn, and they're going to cancel out. Right, we have a frictional force. Right, if the block is sliding to the right, it means the friction force is going to act in the opposite direction. Make it a little bit smaller. So Ff is equal to 9 newtons. Right, and then this is going to be the force of the push, or the applied force. I'll call it Fa for applied force. Right, and so we're trying to find what force is pushed. So we know that the net force equals ma. And again, to find the net force, we either add the forces together or we multiply m times a. Well, in this case, I know what the friction force is, but I don't know what the applied force is. So I can't just add them together. Right? So we know that the net force is going to be 10 times, what's the acceleration? The acceleration is 0 since it's in equilibrium. So we know the net force is equal to 0, right? So that tells me that the applied force minus the frictional force, whoops, let's try that again. The applied force, there we go. Applied force minus the frictional force is equal to 0. Or the applied force is equal to the frictional force, which is equal to 9 newtons. So the applied force is just 9 newtons because it's moving at a constant speed. All right, so let's look at one last one where it's not moving at a constant speed. Right, same 10 kilogram object is moving with an acceleration of 0.5 meters per second squared. Same frictional force. So everything's the same here. So our free body diagram, again, is going to be the same. Normal force and weight cancel each other out. Fw, Fn. We've got force of friction. And we have our applied force acting in the other direction. Right? Again, we know, and the force of friction is 9 newtons. We know that the net force is equal to ma. Again, we don't know what the applied force is, but we do know the acceleration. So we can say it's 10 times 0.5 or 5 newtons. That's also equal to the applied force minus the frictional force. That's going to be equal to 5. Or the applied force minus 9 equals 5. So that means my applied force is just 14 newtons. Okay, let's see how we do that. Same equation, net force equals ma. Sum of the forces equals ma. And we've solved for what we don't know, just like we did with the verticals. All right, so now let's talk about surface friction. All right, friction is proportional to the weight of the object that is sliding. All right, so the more mass it has, the more friction it has, because it's proportional, really, to the normal force. But the heavier something is, the more normal force it's going to have. Okay? It's also proportional to the surface that it's sliding on. The rougher the surface, the more friction there's going to be. All right, there are a couple of types of frictions that we're going to talk about. 2 types. One is static friction. All right, static friction is the friction that keeps something from sliding. When you try to push a box and it won't start sliding, you're trying to overcome static friction. Okay, don't worry about this symbol yet. We'll come back to it later. Okay, and static friction tends to be the bigger of the two that we're going to talk about. The second one is kinetic friction. Right, kinetic friction is what happens when it's actually sliding. Sometimes kinetic friction is called sliding friction. Right, and so as the box is sliding, that's the force that you're having to overcome to keep it sliding. Right, and that kinetic friction is typically smaller than static friction. All right, so let's just look at a couple of examples. Right, take 60 newtons to start a 10 kilogram box sliding. Right, so 60 newtons to start it sliding. So before it started, it wasn't moving. So this must be static friction. How much force would be needed if the box was a mass of 30 kilograms? Well, we know that the frictional force is proportional to the box, to the weight of the box or the mass of the box. So 30 kilograms is 3 times more than 10. So if it's proportional, then the force would be 3 times as much. So 60 times 3, or 180 newtons. What would happen if we needed a surface that was twice as rough? Okay, well, it's proportional to the roughness of the surfaces. So if it's twice as rough, it's going to take twice the force. So 60 times 2, or 120 newtons. Move my body here for a second. Move my head. How much force would be needed if the box had a mass of 20 kilograms and the surface was twice as rough? All right, well, 20 kilograms would be times 2. Twice as rough would also be times 2. So times 2 times 2 would be times 4. So it'll be 60 times 4, or 240 newtons. Let's back down over here. All right. Example 2. Now you push a crate with a force of 100 newtons at a constant speed across the floor. Okay, so now it is sliding. So what type of friction is this? This would be kinetic friction. Okay, what's the net force since you're moving it at a constant speed? The net force is 0. It's in equilibrium. Right? So what's the frictional force? Right? If I push with 100 newtons of force, right? Let's draw a free body diagram real fast. If I push with 100 newtons and friction is acting this way, and the net force is equal to 0, that means this and this have to be equal, right? So the friction force would have to be equal to 100 newtons, but acting backwards to the left. Right? If another crate is placed on top, what will happen to the motion? Okay, so if I put another crate on top, that means I'm basically doubling the weight, doubling the mass. So the frictional force should double because it's proportional. So the new frictional force is going to be 100 times 2, or 200 newtons. And then let's do one more. Right, you push a 40 kilogram crate with a force of 100 newtons across the floor, and it accelerates at 2 meters per second squared. Okay, so what type of friction is this? Again, it's sliding, so this is going to be kinetic. Anytime it's moving at all, it's kinetic friction. All right, what's the net force? All right, again, the net force is either the sum of the forces. I know that I push it with 100, but I don't know what friction is, so I can't just add them together. But net force is also equal to m times a. Well, I know m is 40, and a is 2, so I get my net force being 80 newtons. So when I add up all my forces, it should add up to be 80 newtons. So if I draw a free body diagram, again, I'm not going to write the up and down forces, but they're there. I know that I have 100 newtons this way, and I have friction, the force of friction in the other direction. So 100 minus the force of friction should equal to 80. Well, what do I have to take away from 100 to get 80? Tells me that the force of friction is going to be 20 newtons. If another identical crate is placed on top, what will happen to the motion? Okay, well, if I put a identical crate, that means the force of friction is going to become twice as much. Force of friction is going to become 40. So the acceleration is going to become less. Right, still going to speed up, but it's not going to speed up as much as it did. Right? And then what if you put another crate on top? What if another crate is put on top? Then we're going to go up to a force of friction of 60. All right, 100 is still bigger than 60, but it's going to accelerate even less. All right, so next we're going to talk about what makes up friction. How do you calculate the friction of something? And that'll be in our next video.